So remember, last time I mentioned this result that like if you take n homogeneous polynomials of degree d, 1 up to the n, and each polynomial belongs to this, you take it from the Bombieri-Weil distribution, the expectation of the number of real zeros, so the integral of the function, number of real zeros of the system, is square root of d1 up to dn. Okay, so it's the square root of what happens over the complex numbers. So, and my plan for today is to try to explain in which sense this square root of d1 to the n, it's actually a number which is computed in a ring, okay, as it happens for Bezout. But first, I want to tell you a little bit more on the geometry of the space of polynomials, now moving to several variables of degree d with this Bombieri-Weil distribution, okay? So again, yesterday I mentioned about like systems. Now just want to take an hypersurface and see what's happening. So here is the picture that we have. Again, I prefer to make it like this. So there is the space of polynomials, which I call it maybe P and D. That's our parameter space. And you, inside this space, you have this discriminant, okay, which I call it delta ND, which consists of the hypersurfaces which have a point which is singular over the reals. Okay, so this it's semi-algebraic. It's not algebraic, but if you want to see the complement of this set, you might as well, it doesn't make any difference, take the set of complex hypersurfaces and slice with a set of real polynomials, okay? So you have two things. You can either take real hypersurfaces with a point which is singular, or complex hypersurfaces which are singular and are real, okay? These two things are not the same, right? If you take, for instance, the polynomial x squared plus 1, right? So this polynomial here, it belongs to the complex discriminant and it is real, but it's not singular from the real point of view, okay? But objects of this type, they have higher codimension, so they don't separate the space. So the space is already separated into components if you just consider the real.
Why does it belong to the complex discriminant?
Because it has a double root. So if you take, am I making a mistake? If I take this, sorry, I apologize. X minus I squared. Okay? This.
You should take x squared plus 1 squared.
Yes, sorry. Thank you. Yes. Sorry. You're right. Sorry. I don't know what I was saying. Yeah, of course. Yes. This it's singular from the complex point of view, but it's not singular from the real point of view. Okay? But these things, they have higher codimension, so you don't see them. Okay? I mean, you can see, but they don't play any role when separating the space into components. Okay? It's already done by the reals. Okay, so there is this space here, and well, over each component we have a zero set. Okay, and when you cross one of the components, the zero set change. Okay, this is what happened. So you might wonder how many such possibilities there are. Okay, and there is a nice result by Karlamov, Norekov, and they proved that the number of connected components of this set, it's larger than some constant e to some constant d to the n. Okay, so you get, if you just want to see what are the possibilities when the number of variables is large, it's a way too complicated. So there is no hope you can count, you can tell me exactly what are the possibilities that you can see. Okay, so this somehow like fits into this framework of the Hilbert 16 problem. So studying the possibilities for the zero set of an hypersurface of degree d in Pn, and the way this hypersurface embeds in projective space. Okay, so in this, over each of these open sets, not just the topology is fixed, but also the way it embeds in projective space. It's constant throughout the chamber. And one thing that we know, of course, is that if you take the function that gives you the sum of the Betti numbers of this thing, okay, so like it's a function in the space of polynomials, and you can, it gives for every polynomial the sum of the Betti numbers. So this function is bounded, right? This is something like 2d to the n, so this is so-called Tom Milnor bound. Okay, it's bounded, so in particular it's integrable. Okay, so because it's a bounded function, remember that d and n are fixed, in particular it's integrable. And you can ask what is the integral over your space of this function with respect to the Bombier-Rivale measure. Okay, so we know it's bounded, so the integrand is bounded by, so this is what we call the expectation of the Betti numbers of the zero set. Okay, just the integral over your space of this function. And there is a nice result actually that it's a sequence of results by Amian Gaillet and Jean-Yves Changer. So they proved that there are two constants, C1n and C2n, some positive constants, and such that this function here, it's in between C2n d to the n over 2 at C1n d to the n over 2. Okay, so the integral of this function, so the average number, say, of average total Betti number, it is in between, it is of the order square root of d to the n over 2. And again, because if you want, you can ask how does it compare with the complex case. So in the complex case, the total Betti number of the complex part, this is really of the order d to the n. Okay? So the complex object has a total amount of topology, which is d to the n, but on average, this the real part has total amount of topology, which is order d to the n over 2. It's not clear whether this number here, so I'm going to find some more chalk here. This is okay. It's not clear whether if you take expectation of the sum of the Betti numbers and you divide by d to the n over 2, this sequence is bounded by this result, but it's not clear whether it converges. Okay, so that's an open question. Yes?
So is any of this invariant distribution has the same order as the complex bound?
I'll mention this, okay? So this is when you take the Bombier-Rivale distribution, okay? Of course, there are other probability distributions that we mentioned, right? Other invariant measure on the space of polynomials. So there is this invariant measure, for instance, which we call the L2. If we take the L2 Sn, okay, which means that instead of choosing the Bombier-Rivale norm for building my measure, I take the L2Sn scalar product for building my measure. Well, in this case, the the order, it's not d to the n over 2, it's actually d to the n. And let me observe that like the upper bound, we don't need to prove it, because it's already given by deterministic upper bound. Okay? You just need to prove the lower bound. And the lower bound here, so here the expectation of b, it is of the order, maybe it's in d to the n, and this means it's big O of d to the n, so there are two constants which it's the same that I wrote here, okay? Two constants with d to the n. And the only thing you need to prove here is the lower bound. And the lower bound, it's actually, it follows from some nice work by Nazarov and Sodin, which is actually the basic tool for producing lower bounds of this type, which is the so-called barrier method. So essentially what they show, it is that in every neighborhood of size 1 over d of the projective space, there is a positive probability that your zero set does this, has this behavior. Blue. So this is a neighborhood of size, maybe, let's say the blackboard is RPN, and then I pick a point in RPN, and I pick a neighborhood around this point of size 1 over d. And what they prove is that with positive probability, so the measure of the event I'm going to tell you now is positive, your zero set peaks in the middle, it takes negative values on the boundary, and then it's forced to like pass. So your function, your defining polynomial, has this picture. So it takes a positive value at the center, negative values throughout the boundary of your set. So in particular, there must be a component inside your zero set. Okay? So they just proved that this event has some positive probability. And then what they do, and then this explains the appearance of this d to the n, they cover the projective space with many such disjoint disks. And how many such disks you can fit? Order d to the n, because it's a disk of radius 1 over d, so it has some volume in projective space, say it has volume 1 over d to the n, and then how many such disks you can fit in projective space? Order d to the n. And in each such disk, this will contribute this object some probability. Okay? And this will give a lower bound for the expectation, because expectation is linear. So the expectation of the number of, say, connected component of the zero set, it's larger than the expectation of the number of connected components entirely contained in such a disk. And the expectation of the number of connected components entirely contained in such a disk is the sum of the expectation of the number of connected components contained in each of such disks, and then you just use linearity of expectation to get a lower bound. I was very fast, but just grasp the idea, okay? And actually what Gaillet and Welchanger have shown, it's an improvement of this barrier method. So they proved that like for the Bombier-Rival distribution, if you take a disk of radius, not d now, but 1 over square root of d, and if you choose your favorite embedded hypersurface in the unit disk in Rn, with positive probability inside this disk, so this is the disk in Rpn, this is a disk in Rn, with positive probability, the picture you will see here, it is precisely this one, up to isotropy. Okay? So not just, so Nazarov-Sodin proved that like this thing, this behavior has some positive probability, and Gaillet and Welchanger proved that in this model, every hypersurface arises with some positive probability in a neighborhood of size 1 over square root of d. Okay? So it's a sort of like a probabilistic Nash embedding. Like with probability positive, your polynomial will have as a 0 set in your disk of radius 1 over square root of d, your fixed hypersurface, okay? Up to isotropy, of course. And it's not known actually whether the same statement holds true for, so okay, in this case it holds true the same statement. And maybe I just mentioned that Nazarov-Sodin proved the result for the case of invariant measure, but just on the space of spherical harmonics. But I mean, it's this stated this way was proved by myself and Landberg, but it's just this proof. I really should refer to their result as the result on this blackboard. Yes.
Returning back to the betting numbers and the exploitation, what can we say about the constants with respect to behavior with respect to
the constants? Yeah, that's a good question. So, because at least it allows me to tell you a little bit how it is proved, okay? So,
sorry, what is the question?
The question is what can be said about these constants, okay? It's difficult to estimate these constants, but they're very small, okay? They're very, very small constants, and certainly, I mean, in this case, it makes no sense to make a comparison with the leading constant for maximal hypersurfaces, just because this is d to the n over 2 and maximal is d to the n. In this case, they prove that, that there is this famous quote by Peter Sarnak that a random curve is 4% Arnac. So the constant that they get numerically, it is something like, what is that? 4 divided by 100, so 1 over 25. Okay, it's very small. In this case, it does still make sense to just estimate these two constants. And I think these can be estimated. These, it's totally, I mean, out of reach. It's not clear absolutely how to estimate it. And how is this estimated? Actually, the reason why one can estimate it is because there is another inequality in here before this, okay? Which is an expectation of the number of critical points of a given Morse function restricted to your 0 set. So how do they prove this inequality? They first fit in some Morse inequality. So they just fix in your projective space a Morse function. Let's call it G. It's a fixed one. And then you prove that like for a full measure in the space of polynomials, the restriction of this function to your 0 set, it's still Morse. So in particular, the expectation of the sum of the Betti numbers, it's bounded by the expectation of the number of critical points of this Morse function. Okay? And now there are tools for estimating this expectation. And it turns out that like the leading coefficient here for this computation, it is some integral on the space of symmetric matrices of some modulus of the determinant, and it's integrated, I write it this way, with respect to the Bombieri-Weil measure in the space of symmetric matrices, which is nothing more than the space of polynomials of degree 2. Okay, for which we have already measured. So this is called, by the way, the GOE measure. And this type of integrals, you can estimate it. There is actually an exact formula for this thing. And what is nice about that proof, it is they can also estimate single Betti numbers. The lower bound, again, is achieved by choosing any manifold which has BK, which is non-zero. And the upper bound, you just integrate not on this set, but on the set of matrices with a given signature. Maybe it's I minus. Okay, it's very nice. And what is interesting it is that in the space of symmetric matrices now, these integrals they concentrate near where the signature is half. So the number of critical points, the Betti numbers which are of small, so we correspond to k, which is away from n over 2, they have very, very small expectations. Like all the critical, the critical points come from central Betti numbers. So what the picture I'm drawing is not true because we don't know about Betti numbers, but if these inequalities were exact, so the topology would distribute something like this. Okay, so yours would be n over 2, and this picture here would be bk. Okay, this is k. Expectation of bk. Okay.
This is for Bombieri-Weil.
For Bombieri-Weil, yes, of course. For this measure here, you still have some decay of these, and it's still true also for this measure, actually. So the leading thing, but you don't get an integral on GOE. And again, it's related to the fact that like there is more than one invariant measure in this space.
Where it concentrates?
It's again, it concentrates always like nearby the middle. This is.
How do you compare it with this lower bound that you always estimate to be 0?
Lower bound, sorry, say it again.
You use to be 0 to get lower bound with the expectation of the sum.
I mean, it's the same thing, but so I mean, instead of n over 2, you just have n, okay? And that just gives an upper bound for the number of critical points.
No, I mean, this construction of Nazarov exploits only a B0. Right?
Exploits only a B0, I agree.
But then you said that the measure concentrates near.
The measure for the critical points.
For the critical.
So that's what I'm saying, like this picture here, it's the picture, so I should have maybe said it back. It's what we expect to see, but it's not really this. It's expectation of number, well, I just say this then, maybe it's more clear. Number of critical points of index k. Okay, this is for this picture. Okay, so the Betti numbers should be here under this picture, but we don't know, maybe it could be whatever. Okay, yes?
But so still there is this lower bound which is a constant times g to n over 2 for each Betti number?
Yeah,
Yes.
precisely, yes. Yeah. So instead of this, there's some depending also on k. Okay, yeah. And the same for the L2, except that like you're integrating on the space of symmetric matrices, but with respect another measure, okay? But they all have this the behavior of decay. Okay, so maybe let me tell you 1 second why. So what is happening? So why do we? How can we expect that these results are true? So what is the story behind this situation? And I just want to show you maybe one computation that explains what is happening here in the Bombieri-Weil ensemble. Okay. Remember, so this idea that I'm explaining, I'm taking just a small disk of radius 1 over square root of d, and I'm looking at the behavior of my polynomial in this small disk. Okay, that's what I'm doing. So let's try to formalize this and see precisely what's happening. So take the disk of radius 1 in Rn. Okay, fit this disk. So choose one point, by the way, in projective space, because the distribution is orthogonal invariant. You can choose any point, it doesn't matter. And now fit this disk here on this small disk of radius 1 over square root of d around this point. So this map is just a shrink. Okay. So I have the disk in Rn, and I fit it inside a disk of radius 1 over square root of d in my projective space. And then here, on this disk, I have my polynomial, which, let's say I trivialize the bundle, I can think of it as a map with values in R. Okay? So you see, I'm just rescaling, doing this blow-up procedure, and I get a composite map. Let me call it FD. Okay? It's a random map, of course. It's a random map from the disk to R. So it's obtained in this way. You take, again, shrink, randomness is here, and then you go to R. Okay? You get this map. Let me write down this map, what it is. So maybe I should shrink. So let's write down FD. So let me take as this point, for instance, the point E0. 1, 0, 0. Okay? So let me expand this map at that point. So as a function of this variable. Now the variable here, it's called, let me call it y. Y is the variable here. So fd of y, it is essentially my polynomial evaluated at 1 and then y over square root of d. See, I'm just restricting my polynomial essentially to just, I'm just using the parametrization nearby the projective space, maybe just projecting on the tangent space. Okay, so just doing this. Of course, here it's okay, this is really what we are doing. Do you see what I'm doing here? Is it clear? I have my polynomial, so how to write down this map? Okay, I'm just it's. I mean, there is you can think of it like take instead of RPN, if you want, take the sphere. It's a homogeneous polynomial, and instead I'm restricting the homogeneous polynomial to just this disk on the plane x0 equals 1. Okay? That's what I'm doing. So instead of working in projective space, you can work on the sphere. Okay, so I'm restricting my polynomial to this disk. Okay, in the plane x0 equal 1. It's a disk of radius 1 over square root of d. So this is what you see. But let's write what it is. It's the sum, say, of, there are these Gaussian variables, so there is this Gaussian variable, psi, maybe I write this sum this way, so sum over k from 0 to d, and then there is a sum over the length of multi-index now is d minus k. Okay, so I'm writing the multi-index alpha as beta, so sorry, k, and then some other piece, where k is the power of x0 in my monomial. So it's, there is the Gaussian coefficient, this is psi k beta, so this would be the alpha, and then there is y1 divided to the beta 1, yn to the beta n, and then each one of these it's divided by square root of d, but then, so it's a d to the 1/2, let's make it this way so it's more clear, square root of d, square root of d, okay? So, and these, and there are the weights, sorry. There is the Gaussian variables and these weights, d factorial over k factorial, beta 1 factorial, beta n factorial, everything to the power 1/2. I want you to see properly what's happening. That's why it's not clear. So there is the Gaussian variable, and then there is the weight, d factorial over k factorial, beta 1 factorial, beta n factorial to 1/2, and then there is y1 over square root of d to the beta 1, yn over square root of d to the beta n. Okay? But now look, these square root of d, square root of d, they all go out to, let me just look at this part here. Let's see what it is. So there is a d factorial divided by k factorial, beta 1 factorial, beta n factorial to 1/2. And then there is this 1 over d to the power sum of the beta i's, okay, which is a d minus k over 2. Okay, now look, just collect this part here. So ignore the beta 1, beta n. This part goes to 1 as d goes to infinity. So that means that your polynomial, it behaves as something like sum k from 0 to d, and then sum beta equals d minus k of some Gaussian variable times 1 over beta 1 factorial, beta n factorial, y1 to the beta 1, y1 to the beta d, beta n. There is no d anymore here. D is nowhere. Of course, I'm taking the sum up to d, but you can just take the sum up to some, take it to infinity. But there is no, so the randomness has no longer d in it. And this is why, when you look at this small scale, your polynomial, you can think of it as like sort of a random variable with values in the space of smooth functions on the disk. It converges to something. And this is why you get this lower bound. Okay? And in fact, this is the reason why you also get the upper bound. And to be precise, every possible quantity that you can possibly imagine about 0 sets of a bunch of Bombier-Rival polynomials. Maybe you're counting number of critical points. Maybe you're counting number of points where there is a cusp of everything like this converges to d to the n over 2 times a constant. That's the behavior. Simply because in each small disk of radius 1 over square root of d, the behavior is, it stabilizes when degree goes to infinity. And then you cover the projective space with many such disks, order of d to the n over 2, and you get the result. By the way, the same argument somehow also proves and explains why this model is good for comparing with complex algebraic geometry. Because the same statement is true if you replace real Gaussians with complex Gaussians. Run the same argument. But now, on this, how many such stabilizing disks you need on the complex projective space? Not d to the n over 2, but d to the n. And that's why this model is good for comparing with complex algebraic geometry. So if you cover Cpn, here is Rpn inside, with these tiny disks of radius 1 over square root of d, you need just order d to the n over 2 to cover Rpn, but order d to the n to cover Cpn. And in each such disk, you have this limiting behavior. And now you can essentially compare what are the two quantities. One is over the complex and one is over the real. That's why you get this comparison, which makes it appear this like square root of what happens over the complex numbers. Yes, Shogat?
How much of this is true in the other asymptotic?
0. I mean, okay, sorry, I'm sorry. This is still true. This comparison, it's not, so this part, it's still true in the other asymptotics, but with another rescaling parameter. Okay, not 1 over square root of d, but 1 over d. But it's been proved rigorously only in this case. And there is, so this is not the original proof that Gaillet and Mochanger used. I would say, but this is the strategy that you can use to prove this type of statements in all these models, okay? You have to find an appropriate way of rescaling and then prove that, in fact, what is true is the following. So maybe I'll put it here so that it explains everything. There is this proposition. I mean, that if you take an open set U, which is an open set in the CK topology. Then there exists a constant Cu positive such that as you send n to infinity, degree to infinity, sorry, the probability that Fd belongs to U equals this constant. Okay, so you just fix any open set in the CK topology for the behavior of this map. The open set could be the zero set is diffeomorphic to this one. That's an open set in the C1 topology. But you can consider other open sets, okay, in the CK topology. And this is something that we showed with Michele Stecconi, who was my former PhD student. And once you fix this open set, you look at the behavior of this map on this small disk as d goes to infinity, okay? With positive probability, the map will have your behavior, the one that you've chosen, okay? So there is one interesting thing, which is the existence of the limit here. So this argument, the barrier method, would prove something like it's larger, okay? But actually, you can prove there is a limit distribution. Okay, so in this picture, there is a limit distribution. So that really means, for instance, that the probability of seeing that zero set, okay, it has a limit when d goes to infinity. And by the way, coincides with the probability that what is called this real Bargmann-Fock field has this behavior. But ignore the sentence I just said. Maybe it's just confusing, okay? Okay, so this is about, if you want, it's about the local behavior of your zero set. Okay, so in some sense it tells like you can recollect the global behavior by something which is local. But I wanted to tell you another theorem, still in this circle of ideas. So see. This theorem doesn't tell you about the global behavior. Okay, so what's the interaction between these disks? Okay, it tells that on average the geometry, that this function, the integrals of functions of this type are of the order d to the n over 2. But there is still this question that at least I wanted to address, that you can state. Okay, but now let's look at this space again. That picture that we have above. There are all these many chambers, many open sets. This is a projective space of polynomials, and there is the Bombier-Rivale measure on it. Is the measure concentrating near some of these sets? Are some of these sets larger than others? Okay, so that's a totally reasonable question. So for instance, if you apply this game into the space of symmetric matrices, so polynomials of degree 2 in n variables, so if you do the asymptotic when n goes to infinity, all the measure is nearby hyperbolic quadratic forms. So quadratic forms with more or less half positive and half negative. So the probability that a quadratic form is positive, it decays exponentially fast. Is anything like this true in this picture? Okay, but of course, here remember, like we are looking at the behavior as the degree goes to infinity, not the number of variables, which is what I just said about quadratic forms. And the answer is yes, and it's something that we prove with Dauda Nyang-Diatta, who is in the audience. But let me explain in which sense. So first, observe the following fact. If you take the space of polynomials, you can project this space, let me call fix L an integer, but with the same parity as D. Okay? Now there is the space of polynomials, and I think inside the space of polynomials you can project it onto these subspaces. So polynomials of the form norm of x to the power d minus L times polynomial of degree L. Question? So See, the space of polynomials of degree L sits inside the space of polynomials of degree D for our purposes. Okay? In which sense that you can consider, take a polynomial of degree L, multiply by norm of x to the power d minus L, you get a polynomial of degree D. Okay? So it sits inside this. Okay? And from the point of view of complex geometry, what we are doing is nonsense. Because this has zeros in the complex projective space, but has no zero on the real projective space. So the zero set of a polynomial in here, it's detected by its part of degree L. Okay? So do you understand this, what I'm saying? So inside the space of polynomials of degree D, there sit polynomial of this type. Okay? If you restrict this polynomial to the sphere, for instance, I can really say that polynomials of degree L is a subspace of polynomials of degree D. Okay? Because on the sphere, norm of x is 1. And it's a linear space, and you can take the orthogonal projection. They call it PL in the Bombieri-Vai. So maybe let me tell you in a slightly different way. So I want to argue that these orthogonal projections are nothing but the truncation of a Fourier expansion. Okay? So see, take this picture and restrict it to the unit sphere. So instead of looking at polynomials as homogeneous functions, just look at polynomials as function on the sphere. Okay? So then my claim, it is that this space decomposes as a direct union of these spaces H, N, L, where these are the so-called spherical harmonics of degree L, okay? Which is the same space as restriction on the sphere Sn of harmonic polynomials of degree L. If you do this picture when n is 1, you precisely get the trigonometric expansion. Okay, so spherical harmonics are cosinus of L theta, sinus of L theta, okay, and I'm actually expanding a polynomial, if you want, in polar coordinates, rho theta. I'm throwing away the rho part and just looking at the cosinus theta, sinus of theta, okay? And this projection is just the projection on the first L of these spaces, okay? By the way, notice that most of the dimension of this space, in some sense, suppose that you project even on some L, which is order square root of D, most of the dimension is on the top. Because these spaces have dimension which grow polynomial, so the dimension is on the top on this space, okay? Except in the case n equal 1, where they're all two-dimensional. Okay, so here is what's happening. You take your zero set P, and certainly you can consider this projection. Okay? That's another polynomial, which on its restriction to so the zero set of this polynomial on the projective space is the same as the zero set of a polynomial of degree L. Okay? And you can ask, let's look at the set of polynomials P. Inside my space, okay, I want to look at the chambers, so the set of polynomials P, where the following happens, that the pair Rpn zero set of P, this pair, is diffeomorphic to the pair Rpn zero set of this projection. Let me consider this set, okay? I baptize it maybe E, D, because we are in degree D, and L, because of course depends on the degree I am pretending to approximate. Okay? So it's some subset in this, and it involves some chambers, of course. This property here, it's invariant by continuous deformation. So this thing, it's a union of chambers. Okay? This thing, it's a union of some. So maybe, see for instance, if already L, it's not D, the chamber which contains the maximal things cannot be touched by this object. Okay? So it's a union of some chambers. Okay? Which of course depends on L. And here is a theorem that we proved. That if you look at the measure in the Bombieri vial of this set, so this is larger than 1 minus d to some constant e to the minus L squared over d. Okay? So I want to stare at this inequality and then explain what are the consequences. So you see, if L is too small, it doesn't say much, right? But if L starts being close to D, okay, this exponential part beats this polynomial part, okay? So in particular, if you choose L already of the type some, say, constant b, which should be large enough to be this an, times square root of d log d. So if you project on the space of polynomials of degree big O square root of d log d, this piece here vanishes because the exponential part beats the polynomial part. So with probability that goes to 1, your zero set of a polynomial of degree d, it's diffeomorphic to the zero set of a polynomial of degree square root of d log d. See? And this is really a global approximation. You don't see it from the local thing. For instance, if you choose L to be a fraction of d, okay, with lambda in 0, 1, the decays, it's even faster. So the probability, if you choose L this way, it goes to 1 polynomially fast. If you choose this, it goes to 1 exponentially fast. And now these are some consequences. You see, you can say that the chambers, for instance, where there are maximal components, they have exponentially small measure. Because you can only get them with the polynomial of degree d, but not smaller. But also the chambers where you have a maximally nested arrangement, they have exponentially small degree measure. Because remember how this is proved, that the number of maximal nested of ovals is at most integer part of the over 2. You just take a line and you count the number of points on the line. So the number of nests in the oval cannot be larger than integer part of the over 2. So these things, they're also exponentially small. Okay, so every configuration, every possible structure in this, every chamber which has something that need really the degree d to be realized, this is exponentially small. You don't see it in this picture. And that's interesting because somehow like you see, you can slice this picture, if you want, with polynomials of degree L. And essentially what I'm saying, let's say L we take square root of d log d, already to grasp some idea. What I'm saying it is essentially that there are these induced chambers, okay? And most of the mass in your space is nearby here. But it's interesting because the majority of the chambers, they are not here. So if you just want to remember that boundary I put on the top of the blackboard, that like the number of chambers goes as e to the cn d to the n, there is also a lower bound, okay? And so the chambers that you hit here, there is essentially comparable none of them to the total possibility of chambers. So in some sense, like the possibilities that you can get with degree d are enormously large than the possibility you can get with degree square root of d log d. But these have exponentially small measure taken all together. So In some sense, I think this could be sort of like philosophical explanation why getting these maximal things is so difficult. If you just write a polynomial in the monomial basis and try to put some coefficients in front of it, the chance that you get a maximal hypersurface is 0. But not just 0, which of course is not 0, but it is exponentially small because maximal hypersurfaces in the space of polynomials, they belong to some chambers which are... So maybe I'll finish with one picture, which I don't know how to make it rigorous, but so in some sense the idea is that imagine you have this picture of the discriminant and there is a graph. Okay, so let's say that every vertex here of your graph is one chamber. And then I put an edge whenever two chambers share a common top dimensional stratum of the discriminant. So meaning if there is a generic Morse deformation in the space of polynomials from one to the other, or meaning if there is a curve from one to the other that cuts a discriminant in a transversal way. And there is the graph for, say, degree D. And the graph of degree D somehow sits inside the graph of degree 50D, which sits inside the graph of degree 100D, and so on. And when you pass from one degree to another, the number of vertices keep growing, and it grows very fast. But in terms of measure, it doesn't grow that fast. So when you add these chambers here, the new chambers, when you pass to a new degree, you're adding something which compared to degree square root of d log d or smaller degree have very tiny measure altogether. So I don't know how to make this argument more rigorous than this, but this is the picture that it's happening in this space. Okay, I should stop here for today, for now.